Hi, this video will be about our exoplanet assignment. For the assignment, we chose the planet K2 303b. And now we'll start with our parameters. First of all, we have TT, which is the time the field of vision of the telescope is blocked by our exoplanet. So around 2 hours. Afterwards, we have TF, which is the amount of time for the planet to cross the field of vision of the telescope. Then we have the delta, which is 0.003496, the planetary mass, calculated at 1.71 times 10 to the 25 kilograms, so the mass of our exoplanet. We have the planetary radius, which is at 1.28 times 10 to the 4th kilometers. So from its center to its surface, we have its volume. At the right, we have its density and its gravitational force. So 6.96 meters divided by seconds square. Afterwards, we have its orbital period. So it's equal to 5.7 days. So the orbital period is the amount of time it takes for our exoplanet to make a full rotation around its star. So it takes 5.7 days to do a full rotation. Then we have the semi-major axis, which is the distance from our exoplanet, the distance between our exoplanet and the star. Afterwards, we have the eccentricity, so that determines the amount by which its orbit around another body deviates from a perfect circle. So, yes, 0.1. Inclination, which is at 88.7 degrees. We have the stellar radius, so the radius of the star, and it's around 0.3110 radius of our sun. The stellar mass, which is also around 1/3 of our sun, so at 0.332 mass of our sun. The stellar effective temperature, so the temperature at the surface, so around 3,439.85 degrees Celsius. The stellar luminosity, the luminosity provided by the sun, so generated by the sun. The radical velocity semi-amplitude K, which is the velocity of an object with respect to a given point, is the rate of change of the distance between the object and the point. We have the axial tilt that couldn't be calculated, but which is the angle between an object's rotational axis and its orbital axis. And afterwards, we have the atomic spectra for atmosphere that couldn't be calculated either. At the right, we have the habitable zone range, which is the range of orbit around a star within which a planetary surface can support liquid water given sufficient atmospheric pressure. However, the exoplanet is located away from the habitable zone, so further than the outer limit. Then we have the second parameter. So for the possible composition of the planet, we have that the composition of the planet resembles Neptune, having a very low density of 1.97 grams per centimeter cube. Afterwards, the density is very low for a huge planet of a volume which is 2 times bigger than Earth, which can make us infer that the superplanet is made of gas such as hydrogen and can possibly have presence of helium and nitrogen. The only thing that is different between both planets is that the average temperature is very different. Afterwards, we have the seasons. The seasons are dependent on the position of the planet and its trajectory around its star. For example, we will experience summer, spring, autumn, and winter, depending on the position of the Earth around the sun through the year. For us, it takes 365 days to complete this cycle. However, for K2 313b, it takes only 5.7 days to go around its star. From this, we can infer that the exoplanet is closer to its star than Earth is to our Sun, which is why it's completed its orbital period in less time. This could also mean that our exoplanet might be too hot to be habitable. However, its star is 0.310 the radius of the Sun and 0.332 the mass of the Sun, so its position might still be suitable for life. To verify this, the habitable zone range was calculated using the luminosity of the exoplanet's star. We actually found that at all time during its trajectory, the exoplanet is too far away from its Sun to be considered habitable. Therefore, it is probable that the only season experienced on K2 300 is winter. While there isn't any spectrograph data available for our planet, we can take that the early assumption of the planet being a gaseous planet and infer that its atmospheric composition could be similar to that of a Neptune's atmosphere, which has an atmosphere consisting of hydrogen, helium, and methane gas. And for parameter 3, we have the normalized light curve. So we can see that at 0, it comes the relative brightness decreases and increases after 0, and that's it.